Hello everyone. Today I will be introducing to you our third unit, which is on probability theory. In this unit, we will be building tools, formal tools, to understand how to reason with probabilities. Now, these formal tools will be building on the formal tools from the previous unit on deductive logic, and they will ultimately be used to understand how inductive reasoning or inductive arguments work. So today I will begin by reviewing the distinction between deductive and inductive arguments. This distinction we introduced at the very beginning of the class, I think in the second week. And so we will begin by reviewing that. And so, but to take a step back, in the very first unit, at the very beginning of the class, as I just said, we introduced the distinction between deduction and induction. And then in the second unit, which we just finished, we developed formal tools of propositional logic to understand rigorously what deduction involves. And that is, as we'll see, to review, it involves deductively valid arguments. But as we noted at the very beginning of the class, there's another kind of argument other than a deductively valid argument, which can be good, and that is a inductively strong argument. And inductively strong arguments appeal to probabilities. So today I'm going to be reviewing very briefly the overall point of looking at deduction, and then I'll be motivating why we want to move on to thinking about induction. So in the first part, we will review deduction, then we'll think about why we need more than just deduction in order to capture what is a good argument or good reasoning, and then finally I'll introduce induction, which is what we will be ultimately studying in this unit. So the central concept for deduction is the notion of validity. And validity is something which applies to arguments. So, and hopefully this is a review for everyone. An argument is valid just in case it's logically necessary that if the premises are true, then the conclusion is true as well. An equivalent way of putting that is that validity means that it's logically impossible for the premises to be true and the conclusion to be false. And so we saw many examples with our formal tools where we constructed a joint truth table for an argument. And then to determine whether that argument was valid, we looked whether every row on which all the premises are true was also a row on which the conclusion is true. And that was a way in which we rigorously got a handle on determining whether arguments were valid. So here are some simple examples. The first one is as follows. Premise 1, all humans are mortal. Premise 2, Socrates is human. Therefore, Socrates is mortal. That is a valid argument. So if the premises are true, then the conclusion must be. Another one is as follows. Talon is either in bed or in the living room. Premise 2, Talon is not in the living room. Therefore, Talon is in bed. So this especially is a valid argument. And if we formalize this one in our simple tools of propositional logic, then we would be able to see how this is valid, how every row of the truth table in which premise 1 and 2 are true is also one in which the conclusion is true. So these are some simple examples. This example here involves a certain kind of complexity that we're not able to capture in the simple logic we developed. But this example here is one which we were able to capture. And that is to say that from a premise P or Q and another premise not Q, we can validly infer in our logic that P is true. Now, in addition to validity, which is what we capture in our formal logic, we can also ask whether an argument is sound. Now, what it means for an argument to be sound is for it to be valid, and in addition, all the premises to be true. So, after we determine that an argument is valid, say, we can then ask the further question whether all the premises are true. And if an argument is valid and all the premises are true, then we say it's sound. Now, this is an important notion because if we have a valid argument with all true premises, because what validity says is that if the premises are true, then the conclusion must be. We know with a sound argument, the conclusion must be true. So a sound argument establishes, without a doubt, the truth of its conclusion. So the notion of soundness is important because it shows how we can connect validity and deductive logic to actual arguments that we might care about. So here are two valid arguments. These are valid arguments for the existence of a God. So and these are very famous and old arguments that I've reconstructed here. So the first one is as follows. The universe has a beginning. That's the first premise of the first argument. Now the second premise is that if the universe has a beginning, it was created. So anything that has a beginning was created. Premise 3, if the universe was created, then there's a God. So the idea here is that the God is the person who created the universe. And from these three premises, we validly infer that there is a God. Here's another argument. Creatures as complex as humans could not have arisen through evolution. That's the first premise. Now, premise 2, if humans could not have arisen through evolution, we were created by a God. Conclusion, we were created by a God. So here I've given you two deductively valid arguments. That is to say that if you were to translate these into our formal language from the previous unit, you would see that if the premises are all true, any row of the truth table in which all the premises are true is also one on which the conclusion is true. But just because these arguments are valid does not mean that they actually establish their conclusion. That is to say that logic is not going to tell us whether God exists or not. So if we have these arguments which we have determined are valid, we can ask the further question whether all the premises are in fact true. That is to say, we can ask the further question whether the arguments in fact establish their conclusion. So we can ask whether everything with a beginning had to be created. Or we can ask whether, for instance, very complex creatures and phenomena can actually arise through evolution. And however we answer those questions about the truth or falsity of these particular premises, we have to appeal to actual knowledge about the way the world is. And logic itself doesn't tell us whether, for instance, evolution could give rise to humans, or whether, for instance, everything with a beginning was created. So when we ask about soundness, we're asking about the truth. We are usually asking about the truth or falsity of particular claims about the way the world is. And to determine that, we can't appeal to logic. We have to appeal to empirical knowledge. So, for instance, we could show that premise 1 is false by appealing to the actual biology of how evolution works. So I'm giving these arguments not to try to, convince you that God exists or convince you that God doesn't exist. I'm just giving you examples of arguments that are valid and which people care about the conclusion. And I'm trying to illustrate to you that in addition to validity, which our formal tools can help us with, when we're applying those formal tools to actual arguments, there is the additional question of whether those arguments are sound. That is, whether the particular premises we care about in our arguments are true or not. And to establish whether the particular premises are true or not involves appealing generally to empirical or scientific knowledge about the way the world is. So in doing logic, we have to first separate two parts of soundness, or the two parts of soundness. First, the validity, and second, the truth of the premises. Okay, so again, with soundness, there was two parts. There was validity and the truth of the premises. So it's important that we separate out those two parts. And logic can only really help us with the first part, determining validity. I.e., determining whether, if the premises are true, then the conclusion must be as well. But in addition to validity, true assumptions are essential to good reasoning. That is, in addition to validity, the truth of the premises, i.e., the second part of soundness, is also essential. But as I've stressed, they take various kinds of expertise to identify. So think of, for instance, of the work of a biologist in showing that evolution can give rise to creatures as complex as humans. Or consider the work of a physicist who might show how the universe could have a beginning without being created. But again, in general, the notion of validity, whether if certain premises are true, then other conclusions follow, that is the domain of logic. So determining whether these arguments are valid or not does not take any fieldwork, laboratory study, etc. You simply can apply the tools that we've learned in the previous section to determine whether those arguments are valid. But to stress, just because these arguments are valid doesn't mean they actually establish their conclusion, because in order to establish their conclusion, the premises also must be true. Now here is an example, and this might be an overly complicated example, and for that reason, I am not going to work through it in detail. But the field of mathematics is an area in which deductive reasoning, so reasoning which is wholly deductive, plays a crucial part. So for instance, here is a theorem. The square root of 2 is an irrational number. Now this is a theorem of mathematics. Now, you've probably seen this before, maybe in your high school math classes. In any case, I'm not going to be working through the proof of this theorem, but what I want to flag to you is the way in which a mathematician would go about proving a theorem like this. And the way they go about proving these theorems are by taking small steps or small deductive steps. Okay, so how does the proof go? Well, in outline, what you do is you actually assume that the square root of 2 is rational. So we're trying to prove that the square root of 2 is irrational. It's an irrational number. And here on this slide, I have some definitions of those concepts that you can look at if you need to. So in showing that the square root of 2 is irrational, what you do is you assume that it's rational. And then what you do is you take little small deductive steps and you arrive at a conclusion which is a contradiction. And once you arrive deductively at a contradiction from the assumption that the square root of 2 is rational, you can then know that actually your assumption that it is rational is false. Therefore, you establish deductively that the square root of 2 is not rational, i.e. irrational. So the first step is, for instance, given the assumption that the square root of 2 is a rational number, we know that the square root of 2 is equal to two integers, a and b, such that the square root of 2 is equal to a over b, where at least one of a and b is odd. Okay, so that's just the very first step in unpacking our assumption. And there's a whole bunch of other steps in which we make certain deductions with our knowledge of mathematics to unpack this original assumption. And again, I'm not going to work through the steps in any detail because it's unnecessarily complicated, the details here, but obviously if you're interested, you can work through this yourself. But what's important is that in working deductively through the steps, we eventually arrive at a contradiction. And once we arrive at that contradiction, we are led to the conclusion that our assumption that the square root of 2 is rational cannot be true. Therefore, we have proved deductively that the square root of 2 is irrational. And that is how, within the field of mathematics, the use of deductive reasoning is employed. Now, in the next part of this lecture, in the next video, I will talk about other kinds of good arguments other than ones that are deductive. So other kinds of good reasoning that are not like this model of, say, mathematical reasoning, which we've just looked at. But before moving to that, I would just like to make one point about this mathematical proof here. So despite all its complexity, the way that we prove this mathematical theorem is analogous to the short or the partial truth table proofs that I introduced to you at the end of the final lecture of last unit. So at the end of the final lecture of the previous unit, I told you a way of determining whether an argument is valid or not without having to construct an entire truth table and check every row. That method, in brief, was that you can assume that the argument is in fact invalid. So you assume that there is some row on which all the premises are true and the conclusion is false. And then from that assumption, you unpack it. And if you are able to find a contradiction, i.e. if you are able to show that you are not able to construct a row on which all the premises are true and the conclusion is false, then you have therefore shown that the argument is valid, because your assumption that the argument was invalid led to a contradiction. Now that style of reasoning that we saw at the very end of the previous unit was exactly analogous to the style of reasoning which is commonly used in mathematics and which is used in this case. So in this case, in order to prove that the square root of 2 is an irrational number, what you do is you assume that it's rational, and then you unpack that assumption until you find a contradiction. So the style of reasoning we saw in reasoning with truth tables at the very end of the previous unit was very much in line with overall mathematical reasoning. But as I just mentioned, in this unit, we will be exploring another kind of good reasoning, which is not deductive, which is not like mathematicians typically reason, but instead it has to do with probabilistic reasoning. So in the rest of this lecture, in the next two videos, the next two parts of it, I will be motivating and introducing the notion of probabilistic or inductive reasoning.